Desde los orígenes de la computación, la inteligencia artificial ha sido una de las motivaciones principales de los investigadores. Uno de los principales investigadores en inteligencia artificial hoy en día es Michael Littman. Él estudia cómo con estrategias de premios y castigos de recompensas hacer que la computadora sea mejor interactuando con el ser humano. Hello, Michael.
Hello.
It's very nice, a pleasure to have you here. Let me start asking you, how would you introduce yourself?
How would I introduce myself?
Yeah.
Maybe I should just introduce myself and see how it works.
Yeah.
So my name is Michael Littman. I am currently a professor of computer science at Brown University in the United States in Providence, Rhode Island. It's one of 7 schools in the United States that is older than the United States. And I've always been very excited about computer science. It's something that has meant a lot to me for a very long time. And so I feel really lucky that I get to teach it to other people.
You're an expert in artificial intelligence, or you were invited as an artificial intelligence expert to the conference.
Yes.
But if I had to introduce yourself, I would say that you are a reinforcement learning. Can you explain us what this reinforcement learning means?
Yeah, so what I'd like to tell people who are not themselves in artificial intelligence is that, first of all, I'm a computer scientist. I study how we can design algorithms to make computers do the sorts of things that we want. Within that, I'm in artificial intelligence, which is about getting computers to do human-like things, not necessarily in human-like ways. Then within artificial intelligence, I'm in the subfield of machine learning, which is about trying to get machines to learn to do human-like things through data, through exposure to various kinds of data. Within machine learning, I'm in a tiny little sliver called reinforcement learning, which is about doing that kind of learning for behavior, getting systems to actually act in the world and carry out various kinds of procedures based on being taught.
You're talking about learning and exposing to data to computers, and humans typically are exposed to very little data to extract general rules, to think about things. You get exposed to very small things, and in general, you almost immediately come with a theory. Computers are not even close to do that. So,
yeah.
What do you think?
So, is this you speaking as a neuroscientist?
Well, maybe.
So it is true that the sorts of things that we see, certainly adult humans doing, are really quite remarkable compared to what we know how to do with computers. People can see, so I've never been in Argentina before, but if, for example, someone were to either use a certain word or do a certain kind of practice, like a special handshake that only happens in Argentina, it would only take me that one time to realize what I need to do, how to do it, and even the fact that it is somewhat local to this area, because I haven't seen it in other places. But I'm an adult human. I've had a lot of data. I've had a lot of data. I'm not going to say my age, but decades of data, almost half a century of data. And so it's not quite fair to say that people do what they do based on very little data. It's that data is usually built on top of all this experience that has come before. And so the sorts of things that I'm expecting as a person to pay attention to are the things that I've gotten exposure to my whole life to know that I should be paying attention to.
You're saying this whole data that we are exposed to, but also we have evolution. So we have the cumulative information for hundreds of thousands of years. What do you think are the most remarkable differences between the brain architecture and maybe the computer architecture that makes computer and humans so different?
Yes, well, if I really knew the answer to that question, I would be getting a Nobel Prize right now.
Then?
But no, I think it's a wonderful question, and in fact, I think that one of the things that really stuns me, I'm very interested in the brain. I consider myself to be a psychology groupie. Like, I like to hang around with psychologists and follow them around and listen to what they have to say, but I'm not myself a psychologist. And so I've gone to a lot of talks and I think about these issues a lot. It's really hard. Yeah, one of the things that I think is really remarkable is the way we design computers today. It's very much around this idea that we're going to have this this single thread of control, essentially, that we're going to do everything that we need to do along a kind of a linear progression, which feels like thought to us, at least consciously, but that's not what the brain is spending most of its energy on. There's zillions of things happening all at once, information being processed and reprioritized constantly, and that to me is one of the remarkable differences between brains and computers, is that we write programs in a very, direct, forward kind of way, but brains seem to be all over the place.
Reminds me to a question I have written for this interview, and it's about the Turing test. So
Turing test, okay.
When you read the Turing test from Turing, he talks about a mathematician doing calculus and thinking about which is the procedure that the mathematicians do when they do calculus, and talk about how this can be simulated or emulated by the computer. However, when you look at famous films like Terminator or iRobot or the new one Ex Machina or all these films, you always see the Turing test, or how to distinguish computers with humans using psychology. Can computers act like feeling things or free will or taking decisions? So what do you think about the Turing test and maybe the directions we should be redefining?
That's a very interesting question. So yes, I think these kinds of movies are great, and they do spur a lot of interest and the ability for people to kind of think about things in a new and creative way. We don't spend a lot of time on them in the field actually studying these movies or making some, well, we do try to make some of those things happen, but not the killer robots, because that would be wrong. So the Turing test, which was also in a movie recently.
Yeah.
So then, sort of Terminator. It's Not a Beautiful Mind. What was the movie?
The Turing movie.
Yeah, but it was named for
Enigma
the Turing
Code.
test itself.
Oh,
No, it was called the Imitation Game, which is what Turing called the Turing test, because you don't name tests after yourself. And so, so the Turing test actually has been really significant in the history of AI, but it's not something that people spend a lot of time on now. We're not building programs and then wondering, I wonder if that's intelligent. Let's give it the Turing test and see. The Turing test is more of a conceptual framework for thinking about, more than anything else, what does it mean to be human? And I think from that perspective, the progress in computer science over the last 50 years is sort of remarkable. Computers can now beat human beings at very intellectual games like chess. You can now access online like Wolfram Alpha, which is doing much more sophisticated mathematical reasoning than most people can ever achieve in their lifetime. Not as best, of course, as the true giants in mathematics who are inventing these things, but way more than me and anybody that I know, probably. So I want to say that one of the things that we've learned kind of as a society is that maybe these things that seem super duper impressive and intellectual are actually not the really interesting things. It's like people learning to be like computers and not really the other way around. In fact, what it seems to mean to be human is much more about the stuff that you're talking about. What does it mean to socially interact, to connect with someone, to really be able to communicate with them? And at the moment, it's very cartoony. The way that computers communicate with other computers is they have a predefined language in advance, and then they beep at each other really fast, right, to exchange information back and forth. And they can't, and they don't express anything more interesting than that.
They don't doubt.
They don't doubt. Not in the way that not in the way that people would normally think about it. But computers do have error-correcting codes, right? And so they look at the bits that come in and they say, is this really what was sent? Can I figure out what was really sent from what I heard? So that's a little bit of doubt, but obviously not the kind of human, why am I here kind of doubt. Computers don't ask that question.
So you said you are like a psychology groupie or
Yes.
something like that. So I know you have a lot of interest besides computer science. For example, you are a psychology groupie, or you do juggling, or you dance, you like to cook, to eat, and a lot of things. So why did you choose computer science?
Sure, so all these different things that one can do in life. Why computer science? So I was a computer groupie, as it were. Okay. When I was a teenager, we had a shopping mall in my neighborhood, and they were starting to sell computers. And this was now in the 70s, so this was a long time ago. There was no computer science, degrees or fields, certainly that I had heard of. But I saw these boxes, and they were so interesting. And I would try to stump them. I would walk up to them and ask them, what's 1 + 1? I'd type in, print 1 + 1. It would say 2. Like, yeah, well, sure, everybody knows that. But what about 1 + 1 + 1? And it would be 3. And I'm thinking, that's that's kind of interesting. What is going on inside this box that's letting it answer these kinds of questions that I know how to answer? And so I was kind of hooked at that point. I was 13 years old. I got a computer. I'm interested in a lot of other things, but not the same way. I mean, not the way of like, I really want to try to make a contribution here. I really want to understand and push the frontiers of knowledge in that field.
Would you like to do some juggling here, an improvised performance, or?
Well, I have to tell you, my favorite thing to juggle is oranges, so naranja. So if you can get me some oranges.
Okay, perfect. We have it here. So.
I would be delighted. Now, sitting, on the other hand, is a very difficult problem.
Oh, and do you know how to do it?
No. I mean, I almost fell off of my chair.
Okay.
Let me start with the 3.
Okay, sure.
Actually, let me just start with the 1. So I like juggling oranges the best, and there's 3 reasons for it. 4 reasons for it. The size and the texture are 2. So it feels really good in your hand. It's like the right weight, the right texture. It's also pretty color, so it comes out really well on film. And it smells nice. So you actually like flavoring your hands while you're actually doing the juggling. So, so here we go. So this is me juggling.
We have an expert reinforcement learning juggler.
I can try the 4. I've been working on 5.
Okay.
But I'm
we
glad
don't have 5.
I'm glad you don't have 5.
We don't have 5.
And those are glasses, so I'm going to step back just a little bit. All right. So, yeah, sitting is hard.
Well, all right. Thank you very much.
Thanks.
I listened to your talk in Microsoft, actually, when you were there, and you talked about humor, and now you were talking about that. And what it looks to me is that maybe computers are very good to some things that humans don't, but humans are better than computers in some others. For example, humor. So why don't maybe we should work in this hybrid computation where humans do what they do best, and computers. For this, it looked like we should be looking more to the cognitive science so that computer scientists know what to give humans to do better than computers. So what about your history working with cognitive science? Have you had any approach with psychologists or cognitive scientists or computer scientists that works on cognitive something?
So yeah, I think that's a great question, and that it is, I mean, it's interesting that you pointed out, because in some sense we're already in that world, right? Yeah. So I am a much smarter person because I now have Google at my disposal,
yeah.
Right? And so
that was my next question, actually.
So I seem to know incredible things. How do I do? Wait, 1 second. It's because of my hypothalamus, right? So so we're already sort of technology has always been about making people be able to be better at the things that they are already good at. So I don't think that's all that controversial. I certainly don't want to view it as any kind of competition, that we're trying to make machines that will supplant us. That's not really, I don't think anybody's really making that into a goal. What we're really thinking about is, as you say, understanding what people can do and what machines can do to help. A lot of AI is about trying to make computers do the things that have been hard for computers and easy for people. But that's because I think that's how we drive forward. That's how we actually get new capabilities into the computers.
Think of when they were together, like when you found a route that went from X to Y. All those paths they went through A and B, which isolates them from that whole subtree. It was a bridge, and it's a bridge that now is severed. Try computing when a graph is all connected. You put the neighbors on a list, the open list. So when I try to run a depth first search graph was in the lurch. I guess it means it makes the search that more efficient. But you didn't have to cut that path, drop that singular connection, start a new component. Now each is in a separate graph, so their reachable descendants have been split in half. No, it doesn't change the time, big O, or the clustering coefficient in the social network. I guess that I don't need that though. Now there's just no pathway that can use two nodes. Now there's just no pathway that can use two nodes. Now there's just no pathway that can use two nodes.
So just to finish this interview, let me ask you, which do you think are going to be the next breakthrough in artificial intelligence?
So that's not a small question. That's a huge question.
That's a huge question. Just to finish.
Yeah, just to, just by the way.
By the way,
one
yeah.
last thought. How would you solve the AI problem? I don't know. I mean, there's a lot of stuff happening now that's really interesting. As you heard in the other talk, there's no point in mentioning that. I think that there are things that are missing at this point, and I personally would, I'm going to try to invest some resources in trying to understand better the question of how you create systems that can learn continually. They can learn something, and that can help them learn other things faster. Your example of people before about how fast we learn, I think we learn to learn that fast, right? We start off actually learning not that fast.
Yeah.
And we learn more and more and more, and that lets us learn even better and better and better. And the way we build machine learning systems today, we train up a system we give it a bunch of data, we train it up, and it's done, right? And so that's great because it's much more capable than it was, but it's never going to change again. If you want it to learn more, you can throw away the old system and start again. So this notion that by virtue of having learned something, you're actually in a better position to learn more things, more sophisticated things, to see the world differently, to be able to compare things that you weren't even able to perceive before, is incredibly powerful. And I think at an algorithmic level, we haven't cracked that yet. And to me, if we can crack that, that's a huge breakthrough.
So, Michael, which are your driving motivations around your everyday work?
So a lot of what I do is motivated by the idea that I'd like to try to understand computers better so that they can understand us better. So creating computer systems that can actually interact with us in the real world and have a sense of participating with us in society. I think it's really hard to think about what computational processes that requires. And so I study things mathematically, I study things in terms of the behavior, and I study things in terms of algorithmically, how do we actually create programs that can do these tasks.
And to finish it, now really finish it, if you were talking to a child of 16 years old or 17 years old.
I have a daughter of 16 years old.
Okay, so you're talking to your daughter, and she asked you that she's deciding what undergrad to do, and she's not completely sure of technology or computer science, or what would you say to them to convince that computer science is a great way to go?
So
you didn't do it very well with your son.
No, my son is wonderful. He's an outstanding human being, and he's studying to be a music teacher, which I think is a wonderful thing.
Wonderful.
I think if I was speaking to a generic person who was maybe a little bit skeptical of technology, first of all, I think it's incredibly interesting. If you find it interesting, it's interesting. But there's a lot to know there. There's a lot to really sink your teeth in. There's a lot to enjoy. But I think the thing that people don't necessarily see that's very important to see is how much it has to do with people. I think a lot of people, when they hear about technology, they think, well, I don't know, I like people too much to really get involved in that sort of stuff, hours alone in the lab. And that's not science. Science is a very human activity. Not only are we constantly interacting with other people, but we also, I mean, everything that we do, we're trying to understand things so that we can tell people, so that we can share it with people. It's a fundamentally social activity. And so helping people understand that, no, you're not walling yourself off from the world. You're actually making yourself an integral part of the world. if they understand that and they still don't want to do science, say my kids, that's okay. They at least understand what it is. They're not basing it on a misconception. And that's something that I think is really important.
Okay, thank you very much for this interview, Michael, and we hope we will have you here in Buenos Aires longer and maybe dance tango or things you like. So thank you very much for
I would
coming.
like that very much. Very good to talk to you.
You've got some data. I need to find a rule that can predict. You want a theta that works for any instance that you pick. It's Bellman's curse. The classifier needs to fit the labels. Yeah. You start a search, but training error that you minimize won't generalize. You overfit it, spit it out. Mistakes you shouldn't make. Evaluate the testing set. You overfit it, quit it now. You need another way or you'll regret it. Get it, no doubt. You see the error. Hypotheses are overly complex. You feel the terror. I wish your loss had only been convex. You fit the noise and find it's not a standard deviation. Yeah. And so destroys the chance for you to epsilon exhaust. All hope is lost. You overfit it, spit it out. You won't survive the cut that you receive from Occam's razor. Fit it, quit it now. You just misclassified your last example. Sample, not now. Model selection, a labeled collection that's just too sparse. Bound by the tension of VC dimension too wide. It's the end of the line. Cross-validation could help you find the function that you seek. Profound frustration, you failed because your learner was too weak. You just regressed the cubic to a curve that was a constant. Oh, and now you're stressed, attacked by your support vector machine. Just use the mean. You overfit it, spit it out. You try to prune the tree, but find your set of points is shattered. Fit it, quit it now. It's time to pack it in, cause you've been tested, bested, guessed it, messed it all about. You overfit it, spit it out. You try to prune the tree, but find your set of points is shattered. Fit it, quit it now. It's time to pack it in, cause you've been tested, messed it.
Boosting, bagging, weight decay, a gaping margin saves your day. But what a chilling plot this is, to find the right hypothesis. You let your guard down one small bit, oh no, it seems you've underfit. Like scary films in cinema, you're trapped in local minima. Without a strong and helpful prior, you're doomed to chase a lone outlier. The noise runs through your neural net, bewildering your data set. And if you try to leave one out, the folds you must be splitting. Your algorithm can't resist the plague of overfitting. Ah!